Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is the 45th lecture of the summer 2020 offering of ECE3084 Signals and Systems. In the last lecture, we looked at low-pass, bandpass, and high-pass filter functions that were all second order, parameterized by a natural frequency omega n and a damping factor, also called the damping ratio, which we labeled using the variable zeta. With these normalization factors of omega n squared on the low-pass filter and 2 zeta omega n on the bandpass filter, we had these convenient normalizations of the magnitude of the frequency response being 1 at DC for the low-pass case, 1 at infinity for the high-pass case, and 1 at the peak for the bandpass case. Now, there may be situations where we have a resonance bump in the low-pass or the high-pass case, in which case this 1 is not necessarily the maximum. A little bit later, we'll look at the conditions that result in one of these resonance bumps appearing. And if you wanted, you could create some sort of composite function consisting of some scaling factors on the low-pass transfer function, the bandpass transfer function, and the high-pass transfer function, where you let the zeta and omega naught be the same in each of the individual transfer functions, and that will give you a generic second-order filter with a second-order polynomial in the numerator and a second-order polynomial in the denominator. And you would have the same pole structure, but by changing these various coefficients, you could move the zeros around. For the purposes of getting a handle on things here, I'm going to focus on these individual responses. Since all of these denominators have the same polynomial, let's focus on that polynomial a little bit. So let's find out where the poles land as a function of the damping factor zeta and the natural frequency omega n. I have my handy-dandy quadratic formula that'll make me write minus b, which will be minus 2 zeta omega n, plus minus square root of b squared, which would be 4 zeta squared omega n squared, minus 4ac, which will give me a 4 omega n squared, all over 2. Let's see, I'll be able to pull a square root of 4, which is 2, and a square root of omega n squared, which is just omega n squared out. So here I'll have 2 minus zeta omega n plus minus 2 omega n. That's pulled out of the square root sign. And then under the radical, why is this called the radical? Anyway, I'll have zeta squared minus 1 left over. And this is all over 2. The 2's happily cancel. And then I'm left with minus zeta omega n plus minus omega n square root of zeta squared minus 1. Let's add a subscript p to remind ourselves that these are the poles. And if you want, you could factor out the omega n here and write it like omega n times in parentheses minus zeta plus minus square root of zeta squared minus 1. So that's where the poles are located. So I'm interested in finding out when I get complex conjugate poles. I'll get complex conjugate poles when zeta squared minus 1, the material under the radical here, is less than 0. Because taking the square root of something less than 0 is going to result in me having an imaginary number in my expression. So I write zeta squared less than 1, and I can just write zeta less than 1. So if the damping factor is less than 1, then we refer to this as the underdamped case. And the poles here are going to be at minus zeta omega n plus minus omega n with a j in front times square root of 1 minus zeta squared. So let's think for a second about what the partial fraction expansion is going to look like after you take the inverse transform. I'll have some constant times e to the minus zeta omega nt, and then I'll have something like e to the j omega n square root of 1 minus zeta squared. And then I'll have some sort of complex conjugate term that will have an a star e to the minus zeta omega nt times e to the minus j omega n square root of 1 minus zeta squared. And this will turn back into some sort of cosine with some phase, and it will have a decaying term in front of it. But the main thing I want to point out is this quantity here. Let's call that something. Let's call it omega d. So this is referred to as the damped frequency. Notice that omega d is less than omega n because zeta is going to be less than 1. Of course, it needs to be in order for the square root here to give me something real valued. Remember, I already put the j in front here. So the result of the square root is going to be something less than 1. So the underdamped case will give us oscillations in the impulse response. I'm drawing here the impulse response for the low-pass case. It will decay at some rate as indicated by this zeta omega n factor. But the main thing to note is that the system wants to party. It wants to resonate at a frequency of omega n. And it would do that if there was no damping, if you had this zeta equals 0 case. But if there's any damping, then the system cannot party as hard as it wants to party. It's going to oscillate at a frequency that's less than the natural frequency. And the more damping you have, the smaller that frequency is. And then the sadder the system is because it's not allowed to oscillate as quickly as it wants to. So we've looked at the case where we have complex valued poles. What about real valued poles? Well, that's obviously going to be the case where zeta is bigger than or equal to 1. I'm actually going to split this up into two different cases. One case we'll call overdamped, and this is the situation where the damping factor is bigger than 1, and we'll also have a critically damped case, which is this borderline case where zeta is equal to 1. In the critically damped case, both of our poles land at minus omega n because zeta is 1, so that goes away, and I'll multiply that by omega n, and when I plug in 1 for zeta, this square root disappears. And both poles land at that spot, so this is a double pole. Now for the overdamped case, there's no particular reason to write the poles any differently. There's not a j to pull out, so we'll just use that formula. I would actually like to have some more space over here, so let me move my critically damped observations over. In the overdamped case, the inverse partial fraction expansion is going to look like some constant, let's call it A, times e to the minus omega n zeta, let's say minus, so this will be the pole furthest to the left, omega n square root zeta squared minus 1, all of this times t, ut, plus some other constant with e to the minus omega n zeta plus omega n square root zeta squared minus 1 all in parens times t ut. Let me move this ut up a bit so it's more obvious that it's for that first term. So this will be some sort of combination of decaying exponentials. What about the critically damped case? Well, for that, we'll have an inverse Laplace transform that looks like some constant times t, because of the double pole, e to the minus omega n t ut. And I've just noticed that this y of t here should have some uts. So let's scoosh everything over to the left a bit. So let's put a big bracket here, maybe a big bracket here, and make this all times ut. Okay, that looks really terrible, but you get the idea. Now, of course, all of this kind of analysis is for t bigger than or equal to 0. We're not making any claims about what's happening for t less than 0. So here I've booted up the PZ GUI developed by Mark Hopkins, who's a professor at the Rochester Institute of Technology. And I would like to start by putting a couple of poles at minus 40. That's a single pole. I set the time domain GUI over here to show the impulse response. And since it's just a single pole here, I have a decaying exponential, which is what you expect, and it's a very boring one-pole low-pass filter. Let me add a pole to the same location. Now I have a double pole. So my impulse response, if I look at it, it starts at 0, goes up, and then it decays. Let's see if I can scoosh in on this a bit. There we go. That makes it easier to see. Let me scoosh even more. Scoosh. Let's zoom in a bit. There we go. So here you can see that at the start of the impulse response, the t that is part of the t times e to the minus omega n t, that t is dominating the behavior. But you don't get that climb forever. Very quickly, the exponential takes over and pulls it back down. One thing I want to note about the magnitude plot here is that although I have it on a logarithmic scale in the frequency axis, I'm plotting it on a linear scale on the vertical axis. So it's not really a Bode plot. A real Bode plot has a log scale on both axes. I just find that some of the things I want to point out are easier to see if you're looking at it on a linear scale vertically. Generally, you do want to have both of the axes on a log scale. This is just for particular pedagogical purposes. I like to show things on a linear scale vertically. The other thing I want to note is that I've clicked the Fix DC check mark here. So it's going to constantly change the scaling factor to give it a constant DC value. That makes a lot of stuff easier to see. So for this two-pole low-pass filter, that would be like the omega n squared in the numerator. So let's take the poles and pull them apart. That's kind of fun. But for the purposes of this lecture, we don't want to have these running independently. For the purposes of this lecture, I would like to be able to fix an omega n and then change zeta. And although the GUI will let you do that for zeta less than 1 for the underdamped case, it doesn't seem to have a way to do that for the overdamped case. So something that I know that you probably don't know yet is that for the underdamped case, for zeta less than 1, if you fix the natural frequency omega n and then you sweep zeta, zeta sweeps a circular shape. So to facilitate that, instead of putting a minus 40 here, let me put in minus 40 plus 40j and then divide by square root of 2. So it's still on a circle with radius of 40. So let's add that. Notice that this dips up, it comes back down, and it goes back up. So now I'm going to make sure that I have constrained to constant natural frequency omega n checked, because now I can grab these poles and move them around. If I can get them close to this particular case, I guess that's close enough. This is that critically damped case. And now if I separate them, and let's see if I can separate them. You know what? I think I got close enough to the real axis here that it assumes that I want them to be on the real axis because it doesn't want me to branch these back out. Let me reset all that. So in this range, we have oscillations, as we expect for the underdamped case. But notice if we're close to the real axis, these wiggles are really small. They're too small to see on the scale. We have to go up a bit here to hit the point where you can start to clearly see that it doesn't just go below 0, that it actually comes back up and then back down. Now, if I start pushing it towards the imaginary axis here, once I've got pretty low zeta, then you can seriously see some oscillations going on. And the zeta here is a bit hard to interpret. The zeta here has a % sign on it. So if we see 29.1%, that's really a zeta of 0.29. So down here, we're about to hit the axis. Here we have a zeta of 0.99 something, something, something. So that's pretty close to 1. And as we go out here, you can definitely see some wiggling going on. As we get close to the axis here, you'll see that it's now pretty small. I've got a zeta of 0.03, and it's almost 0. So now if I do hit this point, now I'm at the marginally stable case. And no matter what I give the system, it's going to spit out this sinusoid. Now, if I want to go really crazy, here I have a case of a negative zeta. And notice I never really talked about that, because here we can't even think about frequency response anyway. Here you'll see that we clearly have some sort of horrible expanding exponential. Like the exponential is so aggressively expanding that it just goes, wee! Oh, look at this, 10 to the 307. Okay, let me put it a little bit further down. It's still pretty crazy. At least you can still see an exponential here, but this is going 10 to the 84. Let's go in a little bit more. Let's see. Okay, here, 10 to the 40 is the scale. Positive exponentials are really powerful things, and that's why you should take the coronavirus very seriously. There's lots of folks in charge of public policy that don't understand exponential growth. All right, let's move this back to the realm of sanity over here. Okay. Yep. Let's change that scale. All right. Now, one observation I would like to make here is that we have fixed omega n. We have fixed the natural frequency. And if we were to get this exactly on here, let's actually try that. What I'm going to do is I'm going to delete everything here. Let's say we just put something at 40J. Okay, now you can see a sinusoid. And that sinusoid is wiggling at a frequency of 40 radians per second. So now if I start to dampen the system, we have two effects. One is we do have this exponential decay, and that exponential decay gets notably faster as I start damping the system more. But there is another change. Remember, the damped frequency omega d is not the same as the natural frequency. It's the natural frequency times square root of 1 minus zeta squared. But in practice, something you'll find is that the damped frequency and the natural frequency are pretty close. In any case where the decay is slow enough that you can actually see the wiggles to any extent, if zeta is low enough for you to have a slow enough decay that you can actually look at a number of these oscillations, usually you're in a regime where omega d is awfully close to omega n. It's not as high as omega n, but it's pretty close. So in practice, it usually looks on the scope like you have an oscillation at a frequency of omega n. And for ages, I didn't understand that. I didn't understand that because I had looked at a lot of oscillating systems on oscilloscopes. And in theory, I had taken a systems and signals class, ECE3084 at Washington University, from Professor Jody O'Sullivan, who was a fantastic professor. I had many, many classes with Professor O'Sullivan over the course of my undergraduate and graduate days at WashU. I must have learned that these are different at some point, but I forgot it because I've looked at so many waveforms on the scope where it looks like the signal is just oscillating at omega n. And that's because omega d winds up being really close to omega n, but they're not the same. Now, there's another extremely subtle point. I've been focusing on this time domain response, the impulse response, but we do have this frequency domain plot down here showing the magnitude of the frequency response. Let me grab our poles again and take a look at when we have a peak in the frequency response. So remember, the moment I've left the real axis, the moment I have complex poles, we have wiggles, we have oscillations in the impulse response. But for this underdamped, but not highly underdamped system, I don't have a peak in the frequency response. It's only until I get to this 45-degree point here that I potentially start to see some peaks. So I only get peaks in the frequency response once I go above this 45-degree line. And you'll see it right there. So you'll see a peak start to form. As I continue to decrease zeta, I'll start to get a peak that is sliding towards what omega n is as I get closer to the imaginary axis. And that peak is also becoming narrower and taller. I have to keep going over here to rescale the plot axes. And as I'm getting closer and closer and closer and closer and closer to that imaginary axis, now I'm really close to having that peak at the natural frequency. Let me scale the time domain plot too. And the peak is very narrow and very tall. So there's a lot of music synthesizers that have two-pole filters, either just a low pass, or in some you can cascade a two-pole high pass with a two-pole low pass. It's fairly rare to actually find a synthesizer with a raw bandpass filter. I think the Elka Synthex might have let you employ a pure bandpass response, but most manufacturers didn't bother because a low-pass or a high-pass filter with the zeta cranked way down makes a relatively decent approximation to the sound of a bandpass filter. But in general, the only second-order filters that I'm aware of nowadays that will give you a bandpass output instead of just a low-pass or a high-pass are probably synthesizer modules for a modular system. As one little quick aside, I can move the poles over here, and the plot down here isn't really meaningful anymore because we have this exponentially expanding response. So I don't have a well-defined frequency response. This is just what you get if you plug in j omega and then plot the magnitude. But that's not actually a useful thing because the system's not BIBO stable. Okay, so let me move my poles back over to the left-hand side here where things are saying. And before we go on, I should mention what zeta this is. This particular zeta, that corresponds to this edge case, where if you decrease zeta beyond it, you start to get peaks. That's zeta equals 1 over square root of 2. So that's around 0.707. So I have 3 different interesting cases. We have the underdamped case, where there's no peak in the frequency domain, and we don't have any oscillations in the time domain. There's this zone from zeta equals around 0.707 to 1, where you do get oscillations in the time domain, but you don't get any peaking behavior in the frequency domain. And then I have this zone where zeta is less than 0.707, less than 1 over square root of 2, where I continue to have oscillations in the time domain, and those are even more evident, but I now also get this peaking behavior in the frequency domain. So we've been focusing on low-pass responses. Let me add a couple of zeros here at 0 to form a high-pass response. Okay, so here's the impulse response. You'll notice that the impulse response of a high-pass filter has an impulse in it. And one way to sort of interpret a high-pass filter is as taking the original signal and just subtracting the low-pass version. There's some complexities with that, so take that with a grain of salt. But anyway, the fact that you have this big jump here, that tells you that there's actually a Dirac delta impulse in that impulse response. Okay, so let's play around with the poles here. So down in this zone where zeta is between 1 over square root of 2 and 1, I have wiggles in the time domain, but no peaking behavior in the frequency domain. But if I cross that 1 over square root of 2 line, then I do see this peaking behavior. So here, the resonance bump basically starts over at infinity and very quickly climbs downward to omega n. So as I get close to the axis here, not only do I see very strong oscillations in the time domain, I see a very strong peak in the frequency domain that in the low-pass case went up to omega n. Here in the high-pass case is going down to omega n. So that's kind of fun. So to look at the bandpass case, I'm going to delete one of the zeros. This isn't a Dirac delta jump. This is just a function that's starting at some non-zero number and is decaying. All right, so if I play around with the poles here in the bandpass case, here the peak's always at omega n, so I don't have these peaks shifting around like in the low-pass and the high-pass cases. If I have a relatively high damping factor that's still less than 1, so this is underdamped. This is underdamped, but there's still a lot of damping. I have a fairly wide bandwidth filter. Remember, the peak for a bandpass filter here is always at omega n. It's not shifting around like in the low-pass and high-pass cases, assuming you get a peak in those cases at all and it's not monotonic. So here I can increase this until I get to that 45-degree angle. There's nothing particularly magical about that, unlike in the high-pass and low-pass case where that zeta equal 1 over square root of 2 was that transition point to having peaking behavior. Here it's just kind of whatever. Now as I go towards the imaginary axis here, zeta is going down. I have increasingly strong oscillations in the time domain. And again, the damped oscillation frequency is not the same as omega n, but it's pretty darn close as I get close to the imaginary axis. But in addition to that, I'm getting a much narrower peak in the frequency domain. So here I have a pretty broad filter. Let me zoom in. Zoom, 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 zoom. Now I have a pretty tight filter. let me delete that and go back to the low-pass case. The last game I want to play with this PZ GUI is I want to switch to constrain to a constant damping factor. So I've set zeta to 1 over square root of 2. That's that little transition point where you start to get a resonance bump in the frequency domain. And incidentally, if you build a filter like this with zeta equals 1 over square root of 2, you would call that a 2-pole Butterworth filter. And obviously, by the fact that I've called it a 2-pole Butterworth filter, you can build 3-pole, 4-pole, 5-pole, whatever Butterworth filters. I won't really cover that in detail here in ECE3084. There's whole textbooks and websites you can find formulas for that show you how to design not only Butterworth filters, but all sorts of other kinds of filters like elliptic filters and Chebyshev type 1 filters and Chebyshev type 2 filters. There are some signals in systems class that go into that in a lot of detail, but given time constraints, I don't think that's terribly useful here. You can find out all that stuff if you want. The neat thing about Butterworth filters is for a given filter order, they will give you the steepest response you can get for either a low-pass or a high-pass filter. Okay, so what I want to do is constrain the damping factor. So we're going to stay in this Butterworth land, so just before we get peaking behavior, and we're going to sweep omega n. So when I select that now, instead of moving along a circle, I'm going to run along this 45-degree angle for the Butterworth case. So let's see what happens here. Okay, so now I'm getting higher frequencies. Down here, I've got a lower cutoff filter, and I have some pretty low oscillations. Now let me increase this. As I do that, you can see on the graph below that the cutoff is increasing as I'm increasing omega n. And up here in my time domain plot, you can sort of see it implied that the damped frequency is increasing, although it's hard to tell because it is decaying pretty quickly. Now let's add a couple zeros to get the high pass response. So I can go back towards the imaginary axis. Oh, this is interesting. It's hard to tell that the cutoff frequency is shifting because the value at infinity is shifting. What if I turn off this fixed DC? Ah, there we go. Okay, for the high pass, let's turn that off. And that makes sense because remember for the high pass, we just had that S squared in the numerator. We don't want the GUI here to be messing with any constants out in front. So here we can increase the cutoff frequency and slide back in here and we can decrease the cutoff frequency. You can see that in the dashed line there. And you also see a change in the damped oscillation frequency. But again, it decays so fast that it's hard to tell. So let us keep that frequency, switch it real quick to keep the same omega n, but let me change zeta so I can move outward on the circle. And let's get really close. So we now have a very small zeta. Let's get a zeta of, how about 0.07? That's a really low zeta. So this system is totally partying. All right, so now I have a really narrow, tall bump in the frequency response that's pretty close to what the natural frequency is. And now this is decaying slow enough that you can really see the ripples there. Okay, so with that in mind, let me switch back to constrain to a constant damping factor and see how steep that line is. Now as I sweep omega n up and down, you can see the peak in the frequency domain down here, sweeping up and down as well. And that's pretty close to omega n. And now, if I look at the time domain, because zeta is so low, I can really see that I can have some fast oscillations and that I can have some slow oscillations. Now, a subtle point is that the damped frequency is not the same as this peak in the frequency response. And I'll confess that's something I did not understand until I was preparing to teach ECE3084 for the first time and possibly even the second time. I had always assumed that the wiggles that I see on the oscilloscope were of a frequency that matched the frequency of the peak in the Fourier domain. Not the case. We'll look at that in some detail. But first, just for completionist's sake, let me delete one of the zeros to look at the bandpass response. So here we have a pretty low zeta. So we have a low damping factor that gives me a very narrow filter. And I can zoom this up and down. Yelp. Yelp. Oh, that's interesting. Now, do I want to put that fixed DC back? I'm wondering how it's interpreting this, because obviously it's 0 at DC, but it's thinking about how it wants to do that constant. That's kind of interesting. We'll actually come back to what's happening with the bandpass response in another lecture. I just wanted to do this because it was fun. Let me switch back to constraining the natural frequency, and let's go to a much higher damping factor, so I get a wider bandwidth filter here. And now I'll change the frequency. Let's see, so if I have this fixed DC on, it looks like as I increase the frequency, the peak is going up. But when I turn that off, then it looks like as I move the frequency up, the peak is going down. Okay, so that's enough time spent messing around with the GUI. It's probably more than enough time spent messing around with the GUI, but I find that kind of fun. I should probably get out more. Anyway, so you might be wondering, where do those resonant peaks appear? It's different for the high-pass and low-pass filter, obviously. For the low-pass case, the resonant peak, which I'm going to indicate with a little subscript R here, is at the natural frequency times 1 minus 2 zeta squared. For the high-pass filter, the resonant frequency is at omega n divided by 1 minus 2 zeta squared. And this is particularly interesting because if you'll recall, for zeta less than 1, namely that underdamped case, the damped frequency was at omega n times 1 minus zeta squared, which looks very similar. The notable difference is there's a factor of 2 sitting here. Now, I previously mentioned that for very low zeta, for extremely underdamped systems that are partying hard, the damped frequency is awfully close to omega n for very small zeta. Similarly, for small zeta, the resonant peak is awfully close to the damped frequency. For low zeta, the effect of that 2 is less evident. Now, notice for this formula to make sense at all, what I have under the radical needs to be positive. So this is the same kind of thinking process we used earlier to show that this damped frequency formula only makes sense for zeta less than 1. So we'll have 1 bigger than 2 zeta squared, and flipping this around and putting the 1/2 on the other side would have zeta squared less than 1/2. We'll have zeta less than 1 over square root of 2. And similarly, we need this to hold, that zeta is less than this approximately 0.707 for the high-pass case as well. We don't ask questions about this for the bandpass case because the bandpass filter always has its peak at omega n. So that 1 over square root of 2 is that magic spot where you have the poles landing on that 45-degree line. Now, there is an alternative parameterization for the damping factor called the quality factor, and the quality factor Q is given by 1 over 2 zeta. So similarly, you can convert back to zeta by computing 1 over 2q. So interestingly, this 1 over square root of 2 transition point for having resonant peaks in the frequency response, that's the same if we parameterize things in terms of q, because I'll just have 1 over 2, 1 over square root of 2, and hey, that's 1 over square root of 2. So thinking in terms of q doesn't change things there. Thinking about whether the system is underdamped or not, that is different, because underdamping would correspond to q being bigger than 1/2. So if you're thinking about damping factors, you think about 1 as being the threshold. So if you're thinking about whether a system is underdamped in terms of Q, the threshold is 1/2. But notice, because they have a reciprocal relationship, you're now thinking about underdamped systems as being high Q systems. And actually, I should do the same thing over here. I should indicate that if you're thinking about where that resonant bump is happening, you're looking at high Q systems. So control theory engineers tend to think in terms of the damping factor, because if you're dealing with control systems, usually you don't want an underdamped system. If you imagine an elevator where the elevator went to where it's supposed to get to, but then goes a little bit up and then goes a little bit down and then goes up and then comes back down, that would not be very good. Your passengers would probably vomit. So if you're building control systems, usually you're trying to get to where you're going, but not have these oscillations. But people who deal with filter design, either in RF or in audio, are often then thinking about trying to develop highly underdamped systems if they're building something like a bandpass filter so they can have a very tight frequency response, in which case they would want to have a high Q quality factor. So it's just a matter of viewpoint in terms of whether you want to think in terms of Q or zeta. You can easily map from one to another. One thing about zeta that's convenient if you are writing a textbook is that it's in line with the rest of the symbols in these expressions. You will find that there are many synthesizers that will have a knob labeled Q, and if it's a synthesizer with a second-order filter, and there's a lot of them out there that have second-order filters, it is this Q. So you can go to your Sam Ash music store or Guitar Center or whatever, or your local music store if there are any left that aren't part of a chain, and you will find synthesizers that will have knobs on them that are labeled Q. And that's a knob the musician can turn, and this isn't some weird thing that the synthesizer designers made up. It is this Q. Sometimes you'll see it called resonance or regeneration or emphasis, but it's the same kind of idea. So the first semester too that I taught 3084 and many of the earlier semesters of my analog circuits for music synthesis class, although it had a different name back then, I went through the derivation of these resonant peak locations. I'm not going to go through the details of that here because it's a bit tedious, but you can look in the textbook if you would like to see that. So if you've lasted this long through this video, thank you. We're almost done. But before we go, let me point out one more thing. If you're wondering why the poles traverse this circle for the underdamped case, remember that if zeta is less than 1, I wind up with this complex conjugate pair. So I can put the j out in front and write this as 1 minus zeta squared. So here I have a real part, and over here I have an imaginary part. And if I look at the magnitude of what this vector is, well, it's going to be the square root of this minus zeta squared plus square root of 1 minus zeta squared squared. And that's going to give me a zeta squared plus 1 minus zeta squared. It is really late at night. At this point of the evening, I appear to be incapable of writing equations with a well-calibrated horizontal orientation. Anyway, this all cancels and I wind up with 1. So multiplying it by omega n, I have this circle with this radius of omega n. And remember, for the critically damped case, that's where my poles land. Whew, that was a lot.